So welcome everyone to our final seminar of 2020. We're very pleased to welcome today Mike Lockwood, who is a Professor of Space Environment Physics at the University of Reading. Mike continues to have a highly active career with over 300 refereed publications, and Mike's achievements have been highly recognised by numerous international awards, including, just to name a couple, the Gold Medal from the Royal Astronomical Society, as well as being elected as a Fellow of the Royal Society. So today, Mike will be speaking on the semi-annual and universal time variations in the magnetosphere. So I'll hand it over to you, Mike.
Thanks very much, Jasmine. I shall try to calm down now. Okay, I'm going to, in this talk, try and make things a bit easier for the questions. In the bottom right-hand corner, if I press a button, there it is, written on the dark side of the moon in this eclipse photo, is a page number. So if you have a question, if you jot down what number page it was on, I can find it quicker. So what I'm going to be doing is talking in and around, about and around these patterns. Okay, I just wonder if I can get rid of the windows. There we go. So these are what we call time of day, time of year patterns. They're showing average geomagnetic activity quantified by a given index as a function of the fraction of a calendar year, F here, so time of year along the x-axis, and universal time along the y-axis. And this is a northern hemisphere index. This is a corresponding index in the southern hemisphere. And AM, M stands for mondial, global, is the average of the two, basically. And these are wonderful images, indices. They go back over 60 years now, every 3 hours, and they're made to extremely high quality. They are by far the best indices to be using for this purpose, and actually many other purposes as well. I'll come on to that. Okay, when we look at these plots, we actually see three different variations. If we look as a function of the time of year, then you can see these peaks piling up at the equinoxes. This is a semi-annual variation. It's been known a long time. It was first published by Broun back in 1848. And we have a good theory for that. But the word good needs qualifying, a lot of qualifying, but it is a good theory. If we look in the universal time dimension, there are actually two variations. Universal time variations were first noted by Bartels just under 100 years ago. And the first of these two variations, universal time, actually does vary with the time of year. And that combination gives you this hourglass-like pattern that we call the equinoctial pattern. Okay, but if you look closely, it's also called, oh dear, sorry. If you look closely, you can also see there is another UT variation with a minimum that doesn't depend upon the time of year. You can see it clearly here in the southern index with a southern hemisphere index with a minimum around 6 UT. And it is here in the northern hemisphere and therefore also in the global index. I should have mentioned, by the way, this equinoctial pattern, as we now call it, is also called in the literature the Mackintosh pattern, after Douglas Haig Mackintosh, who first published it in 1959. So we have these two universal time variations, and we have no accepted theory on what causes those. There are proposals, but there's no consensus as to what causes the UT variations, even though we've known about them for almost 100 years now. Before I carry on, I'd just like to dedicate this talk to two very fine space scientists who were both extremely kind to me when I first started out in the field. They both unfortunately died young, and Chris Gertz was shot by a deranged student, a student who couldn't accept not winning a student prize. And as we've seen in world politics recently, not accepting defeat is not always a good thing. In Chris's last paper that was published posthumously, he talked about pressure balance in the tail, force balance in the tail. He was on to something that I think was correct, and we would have got there a lot sooner if he hadn't been killed. On the left, you have Annick Bertellier. Annick died young of cancer. She did a lot of work on the Macintosh pattern, and she was almost unique in understanding that there was something we didn't understand about it. And as well, Annick's great legacy is those indices that I talked about. When what is now the International Service for Geomagnetic Indices moved from the Netherlands to France, to Strasbourg, her and her colleague Michel Monville took over the management of it, and she threw herself into the service of the international community. And those wonderful indices are very much her legacy. Okay. So I mentioned we have a good theory. It's actually a brilliant theory. It's absolutely brilliant. It's correct because it's correctly based on two correct facts, but it doesn't work how everybody thinks it does. And that's really the main point of this seminar, is that the Russell-McPherron effect works, but it doesn't work the way you think. And that has significant implications. This theory, the facts it's based upon are that the interplanetary magnetic field at Earth is oriented with respect to a solar frame, with respect to the solar rotation axis. But the coupling of solar wind energy into the magnetosphere to give us space weather, that depends on the orientation of that field in a frame that's ordered with respect to the geomagnetic field. And that's the origin of the Russell-McPherron effect. We use two frames. We use GCS-EQ, so geocentric solar equatorial, not ecliptic, so not GSE, and GSM, and they share the same x-axis. They point from the center of the Earth to the center of the sun in both cases. For GCS-EQ, what you do is you rotate the z-axis around until it's aligned with the projection of the solar rotation axis. And for GSM, you rotate it around until it's aligned with the projection of Earth's magnetic axis. And I'm going to call the angle between those two reference frames, the rotation angle around the x-axis that you use, beta. So now, what happens is Earth's rotational axis is fixed in inertial space. And so as we orbit the sun, once a year, it tips towards the sun and away from the sun, giving us the seasons, of course. But the magnetic axis is offset from the rotational axis by about, at the moment, 10 or 11 degrees. And that rotates around every 24 hours. And those two factors give us a time of year variation and a time of day variation. So if what Russell-McPherron discussed was that the field here in GSEQ doesn't have any Z components. It lies in the YX plane. And so the sine of this angle beta gives us how much field from the Y component we convert into southward field in the GSM frame, that being what controls geomagnetic activity. And essentially that gives us this characteristic pattern, because this angle of the beta is a maximum here at the March equinox when at around about 23 UT, when the magnetic axis is oriented like this. I should say we're here looking at the Earth from the sun. And you can see we get the maximum beta, and that gives us this maximum here in March and about 23 UT. Whereas at the other equinox, the rotation axis is tipped this way. The precession, we get the maximum deflection about 10 UT, and we get this peak in September around 10 UT. And this is the Russell-McPherron pattern. And you can see immediately that although it's given you a nice equinoctial variation with peaks at the equinoxes, the UT variation is all wrong compared to the data. Okay, so now there's a key point about the Russell-McPherron. At the March equinox here, it takes a negative BY in GSEQ to give us a southward component. So this peak arises out of southward, out of negative BY, whereas for the September equinox, then we actually want a positive BY to give us a southward component. And so the September peak arises from negative BY, positive BY, beg pardon. And those two BY distributions are roughly equal in their occurrence. This is 22 years, a whole hail cycle. I'll explain why I've used these particular years later on, but it's a whole hail cycle of 1 minute data. And you can see the distribution is just about symmetric. There's slightly more negative BY than positive, but it's very slight. And if we actually look on a basis of individual Carrington rotations, we find that that ratio fluctuates around 50-50. There is a bit of a consistent variation with the solar cycle and with the polarity of the solar polar field. But it's about 50-50 all the time and at any time. Okay, so we're going to be mixing up the two BY polarities all the time. So how does the Russell-McPherron work? Well, as I've said, it already assumes that BZ is in GSEQ is 0. And so the clock angle, if you like, in GSEQ is 90 degrees. And it uses, Russell-McPherron used what B south as a half wave rectified BZ component. So B south is minus BZ, where Z is northward in GSM, when you have southward field, and when it's northward, it's 0. And that, just the angle dependence gives us this pattern here. Okay, and negative BY is giving us this peak, and positive BY, oh dear me, I do beg your pardon, it's giving us this peak. So I'm going to call the peak that is enhanced the favored orientation of BY for a given equinox, or the favored equinox for a given BY polarity, and the one that isn't enhanced, the unfavored peak, okay, the unfavored equinox or BY, that combination. This division by BY is absolutely unique to the Russell-McPherron theory. Okay, nothing else will do this for you. So what does give us this equinoctial pattern? And the answer is the dipole tilt. Bartels knew this back in 1925. He postulated the dipole tilt was having an effect. So this is the angle between the magnetic axis and the x-axis in 3 dimensions. So it's quite like the angle that you use in the Russell-McPherron effect, but that's only a clock angle. It's an angle of rotation around the x-axis. What's different about the dipole tilt angle is the angle of tilt towards or away from the sun is also included. Okay. Now, why should that matter? Well, there's a whole bunch of theories in the literature, and I don't have time to go through what's wrong with each one of them one by one. What I am going to do towards the end of this talk is try to persuade you that the answer lies in the effect of the dipole tilt in the ability of solar wind dynamic pressure to squeeze the near Earth tail. I believe that that is the cause of the equinoctial effect, but that's only just been published, and that's certainly not a consensus view as yet. There is one of this list that I do want to take a look at, though, straight away, because it is the one that people think is the, and there are some quite important people who've pushed this idea, that what is really happening is you have a dipole tilt dependence on the dayside reconnection rate. Now, that is actually a very radical suggestion, because it's basically saying that any paper that used the IMF orientation in GSM is wrong. Okay, you shouldn't be using GSM. GSM does not allow for the dipole tilt toward or away from the sun. It just deals with the clock angle. So all those papers, and goodness knows how many papers there are since the early 1970s that use GSM, I can't imagine. So it's a very radical suggestion. Fortunately, I don't think it's right. The suggestion, the proof for it largely comes from looking at numerical MHD models of the magnetosphere. And what you have here is 3 simulations for identical cases, just with fixed dipole tilt, so not rotating as it normally does, fixed at a certain value. And here you have the equinox case with no dipole tilt. Here you have Northern Hemisphere summer and Northern Hemisphere winter. And what is for sure is that the reconnection site moves. It moves towards the winter hemisphere compared to this, for this case, where it's in the magnetic equator. But one of the things that you'll notice is that because we have this draped field in the sheath, draped over the nose by the slowing of the sheath flow, then it makes very little difference to the magnetic shear across the reconnection point. It's almost identical in these 3 cases. Okay. And in fact, if we look at the reconnection line, our best estimate, there's always numerical errors, but our best estimate of the reconnection voltage in this case is 89 kilovolts, whereas for maximum dipole tilt, it's 85. So there is about a 5% minimum to maximum variation in the reconnection predicted by these models. Why don't I think that's the cause of the equinoctial pattern in geomagnetic activity? The reason is that if I look down at the base of these field lines down here in the dayside cusp regions, I cannot see the equinoctial variation. However, if I look at magnetometers that are underneath these night side field lines, particularly in the substorm current wedge, I do very strongly see an equinoctial variation. So that is not consistent with the idea that the variation is arising through the dayside reconnection rate. There are a number of papers that show this. I'm just going to pick one of the most recent ones. This was by Aude Chambourdeau. She took the AM indices, beg your pardon, and split them into 4 6-hour MLT sectors that are given here. Now, if we look at noon, you can still see the equinoctial pattern. We kind of would expect that as leaking through from elsewhere. It's stronger at dawn and dusk, but it's strongest at midnight. And the variation of this equinoctial pattern for the noon index is 24% minimum to maximum. So that's 5 times more bigger than the variation in that we're getting from the model in the reconnection rate. And when we look at the size of this pattern on in the midnight sector, it's actually 70%. So that's 14 times bigger than the variation in the reconnection rate. As I say, this isn't the first paper to point this out. Lyatsky et al. Found it in the AE indices, and they're perfectly correct. I don't agree with their interpretation as to what's going on, it being a conductivity effect for a number of reasons, but I won't go into that. And Ivan Finch did the study that I was talking about, where we looked at cusp field lines and the substorm current wedge, and he found that this pattern was arising in the substorm current wedge. Okay. Just for completeness sake, there is a third theory that dates back to 1912 that says geomagnetic activity varies with the heliographic latitude of Earth. And this varies through the year because of the inclination of the ecliptic plane relative to the solar magnetic plane. And it happens to peak just about, sorry, my phone's going off. It happens to peak just around about the equinoxes. And because it doesn't depend on how the Earth is oriented, there's no UT variation. And so you get this axial pattern, we call it, where there's no UT variation, but there are peaks near the equinoxes. Now, people have tried very hard. These differ slightly in their timing of the peaks for these 3 mechanisms. And they've tried very hard to use this to distinguish between the mechanisms. The problem with that is that space weather comes in events, and those events are quasi-random in their precise occurrence time. And so you need an awful lot of data to average out that randomness and define the difference. It's possible that you can tell the axial effect is not working from that. That's just about resolvable, but you can't tell the difference between the equinoctial and the Russell-McPherron effect that way. But just one other point about the axial effect, you have to be careful about timescales. So what I've done here is I've taken a Russell-McPherron pattern in 1 hour data, and I've averaged that data over 6 hours. It's synthetic data. And the peaks have gone down a bit, but it's still recognizably Russell-McPherron in form. And the peaks have been stretched out a bit. If I average over 12 hours, the pattern just becomes axial. And why that matters is that indices like DST do show an axial pattern. But if you look at DST, you find it has a long response time to the interplanetary medium, about 16 hours integrated up. The previous 16 hours integrated up is the best way of predicting DST. And so, of course, you're going to average out the UT variation and see an axial pattern. Doesn't mean it's axial in terms of the axial effect, but you do get an axial pattern just out of averaging and timescales. So be careful, not everything that looks axial is axial. Now, I've said Russell-McPherron really works, and it really, really does work. What you have here on the top is the power input to the magnetosphere. I'll tell you how we get that in a bit. But it's been divided by the prevailing polarity of By. And it's, you can see, giving us a beautiful Russell-McPherron pattern, okay? And this is the geomagnetic index, AM geomagnetic index, and it's not quite as good, but it's still recognizably Russell-McPherron. What's interesting is if I take all the data and average it together, sorry, didn't mean to do that, which I've done here. Firstly, the pattern is much lower amplitude, and I notice the scales have changed by a factor of 5, around 1, but also it's really ratty. Okay, it's really not a clear pattern, whereas it is when you break it out by By. And in AM, when I do that, I get the equinoctial pattern instead of a Russell-McPherron pattern. Okay, so very strange. So it's working, but it's not working. This is in average values. If I take the occurrence of large events, and I'm here looking at events that exceed the 95th percentile of all data, and I'm using all data after 1995, then I get the same thing exactly happening. So this happens for the occurrence of events and for averages as well. Now we get a clue as to what's going on. If we take a look at the top here, you have those patterns for power input to the magnetosphere, and underneath you have the model that I gave you from Russell-McPherron, and they look pretty damn good. But notice the scales here. Okay, we're oscillating by about 40% around unity in the top scale. It's because it's been normalized, whereas the prediction's going between 0 and 6.6. So if I scale the predictions onto the data and then plot them on the same scale, so I fit and then scale, I get that. And then we begin to see why things are different. There's a very important difference now between these predictions and the data, sorry. And that is, it's very sensitive. It's a new computer and it's a very sensitive keypad, and I haven't got used to it yet. That essentially in the unfavored equinox By polarity combination here, we have just a flat minimum. Whereas in the real data, we have a minimum feature that is as deep as the maximum feature, the enhancement. And we can see it here as well, okay? And that's a very important difference between the two, which actually gives us a big clue as to what's going on. I'll come back to that. Now, the other assumption that I want to just look at briefly with Russell-McPherron is that they assume that the clock angle in GSEQ is 0, that there's no north or southward field in GSEQ. And if you look at 22 years worth of the clock angle in GSEQ, you can see, oh dear, every time I try to use the pointer, you can see that the most common value, the mode value of the distribution of clock angles is 90 degrees. you can see that the average value is 90 degrees. However, it's not the only value, and there is this distribution, and the occurrence of, I'm going to have to stop using the pointer, I'm afraid. The occurrence of purely northward field at 0 clock angle is only about half that of the mode, and likewise purely southward field in GSEQ is half as common as 90-degree clock angle. So why does this matter? Well, essentially, this is a plot of the occurrence of BZ in GSM as a function of BZ in GSEQ. And you can see that it's lining up along a 45-degree line. So this first plot here is for all data. And Russell-McPherron say there's no BZ in GSEQ, it's 0. And so that tells you that we're getting that much southward field out of the Russell-McPherron effect. But we're getting much larger values down here in this quadrant because we've got southward field in GSEQ. Okay, so the sun is throwing southward field at us. It's not just being converted by the Russell-McPherron effect. And if we go to the top 5% of events, that's even more true. If we go to the top, that's top 10%, top 5, top 1. And now almost all the events are cropping up down here. This is by AM. This is sorted by the AM response. And you can see all the large AM events are requiring large southward field in GSEQ, nothing to do with Russell-McPherron. Okay. Just to try and work out what's happening a little bit more, this is a plot, a type of plot I'm going to show you several of, and it's looking at the increase in B south that I'm getting by converting from GSEQ to GSM. In other words, it quantifies the Russell-McPherron effect. And I'm going to look at that as a function of this beta angle. Now, this angle I'm going to define as positive for the favorable orientation of BY and negative for the unfavorable orientation. And Russell-McPherron used this half-wave rectified idea so that when the field is northward, you don't get anything, but then it varies linearly for southward field. But this was for their assumed value of the clock angle. So what is the actual dependence on clock angle? And here you see them every 10 degrees, the same plots. And when the IMF is strongly northward in GSEQ, so we're looking at this yellow part of the distribution, it doesn't make any difference. But then you can see the the half-wave rectified southward field starts to come in. This is the situation that Russell and McPherron actually describe. But as we go on, when we get to about 110 or 120 degrees, the enhancements we're getting for the favorable orientation of BY are actually getting smaller than the decreases we're getting for the unfavorable. Okay, and in fact, all along the bottom row here, the net effect is a decrease. And if you've got purely southward field in GSEQ, then it can only get worse. The rotation can only make it worse. So people say, oh, but the Russell-McPherron effect always helps. No, it doesn't. If you've got large southward field, the Russell-McPherron effect actually decreases the geoeffectiveness of the IMF rather than increasing it. And yet we still get large events and average activity enhanced at the equinoxes. Okay, and we know large events are caused by large field, large clock angles in GSEQ. So there's something very strange going on, and Russell-McPherron does not explain the occurrence of large storms. It explains the average values and explains weak storms, but it doesn't explain the occurrence of large storms. Now, a skeptic will say, ah, yes, but you've used B south, and that's not a very good coupling function. And I'm thinking, well, yeah, that's what Russell-McPherron used, but yeah, you're right. We know a skeptic will say that because we had a skeptical reviewer on the paper, and that's exactly what they said. And so did it again, but this time used a better coupling function, this sine squared B sine squared to the power 4th clock angle over 2 in GSM. And to actually work out which is the best IMF orientation factor, there's actually a procedure that was laid down by Vassilounis et al. I'm saying can you hear me still?
Yeah, yes, we can hear you.
Okay, I'm getting a notification that my internet's gone slow again, so I was a bit worried. Okay.
Oh, we haven't well, I haven't noticed any change.
Okay, good. Okay. I'm not slowing down. I can't afford to. Okay, Vassilounis et al., they laid down how best to do this. Okay, I can't go into the details, but this has been done for the SML index here. But I get exactly the same answer if I use AM or any other index. So now, if I take these data and I look at the half-wave rectified dependence on clock angle, it's this. And you can see it's not a very good fit for weakly northward IMF or even in the ecliptic. And the sine to the 4th theta variation, and incidentally, it should be to the power 4. Variations from that are nearly all due to overfitting, which is something I shall talk about in a bit. But we get a much better agreement with sine to the 4th theta. So let's go back and repeat those last plots for sine to the 4th theta. And we do get kind of the same behavior. The Russell-McPherron effect is kicking in for weakly northward field now. We're getting more enhancements for the favorable than we get decreases for the unfavorable. But again, around 110, 120 degree clock angle, that balances out. Along the bottom here, we have net negative effect, and we have only negative effect for purely southward field. So it's not to do with the form of the coupling function we've used, that it is inherent in Russell-McPherron, okay? Now, an important point to look at here, this is AM averaged up by the two BY polarities, okay? So this is BY positive with the open circles and the triangles are BY. Sorry, one of those is wrong. Okay, that's got to be BY positive. That should be BY negative. I do beg your pardon. That's negative there. So one of the important points is that the increase we're getting for the favorable BY polarity at each equinox is greater than the decrease that we're getting for the unfavorable. And that means when we average the two together in a 50-50 mix, we get an enhancement. And that's very important. That's where the semi-annual variation comes from, okay? That the enhancement for the favorable polarity must exceed the decrease for the other. And now you see why I stressed that that's not what's the difference between Russell-McPherron and power input to the magnetosphere. And then we do see these peaks, not only in the average values, but in the occurrence of the top 10% of AM events, top 5%, top 1%, okay? That is not coming from B South in GSEQ. If we look at the southward component, the average southward component, there are no peaks at the equinoxes in either the average value or in the occurrence of large southward values in GSEQ. So although we've got an equinoctial variation and it's not Russell-McPherron, it's not the occurrence of CMEs with large southward field in front of them or anything like that. Okay, so something else is happening. Now, I want to just step back a minute and talk about the indices. I praised ANIC's indices quite rightly. AM is put together very carefully. You have a ring of stations at constant geomagnetic latitude in the north that is really very homogeneous. Because of the South Pacific here, you have a problem doing the same thing in the south, but there's a very clever use of weighting functions to allow for the fact that your spacing is not uniform in the southern hemisphere. And it really works. If I look at AM as a function, its response function, now this comes from the modeling work that Ivan Finch did, where you model the response of an individual station as a function of essentially conductivity and how far away from the auroral oval you are, the midnight auroral oval. And that means that it's a function of universal time, a function of time of year, and a function of the level of geomagnetic activity, because the auroral oval will expand to lower latitudes when activity is higher. So I've here plotted the response, and when you've got it for one station, you can combine those responses in the same way that you combine to make the index, and you've got the response of the whole index. And for AM, it's beautifully flat. There are variations in there, but they're less than 0.1%, okay, at high activity levels. If we come down to very, very low activity levels, then the lumpiness in our observing network starts to show through just a little bit, but it's not much at all. I want to compare that to the other planetary index that's used, although I can't for myself work out why, which is KP and AP, because they use this network of stations. It's very Eurocentric. There's a few in North America and a couple in Australasia. So the geographic distribution is awful, and they don't particularly mind because of the way it's compiled. What you do is you take every station and you say, okay, it saw this, and you use lookup tables that actually aren't based on a lot of data in many cases, that are a function of time of day, time of year, and activity level, and you map back to a reference station. You essentially say, what would Potsdam have seen? And then you average them all together because it's all Potsdam data. That's fine, but it means you're going to imprint upon the index the response function of Potsdam. And that's what you get. So if we look at the same plots for AP, we have these very large 10 or larger % variations with both universal time and time of year, okay? AP and KP are totally unsuited to this sort of work. It has to be AM, okay? And I think this is true of a lot of other work as well. So personally, I always use AM and I don't use KP. Does it work for the north and south indices separately? Actually, yeah, it's still pretty good. At high activity here, it's still nice and uniform. At low activity, we start to see the conductivity effect of the seasons begins to affect things, but it's still only a plus or minus 2% variation. Okay, so it works for the two hemisphere indices separately. Now, the other thing I just want to cover in a general way is coupling functions. Coupling functions are combinations of interplanetary parameters designed to predict geomagnetic activity or terrestrial space weather. And in general, they have a form like this. They take all the supposedly relevant factors and give them an exponent. So we end up with an exponent on each of them. This is the mass density of the solar wind. And so you can end up, if you do that, with 4 parameters to fit. Okay, some of them are simpler than that. I mean, the simplest one is just the IMF or BV squared, or all of these are in the literature. Okay, but there's a big problem with getting nice and complicated like this, with having all these free fit exponents, and it's something that we don't consider enough in space physics and space weather, and that's overfitting. So what you're doing when you overfit is you've got so many free fit parameters that you start to fit the noise in the data. And that's a real problem because it means that your fit is not robust. You go from your training data to test data or prediction data, and you find the noise is different, and so it's not working as well. This problem is well understood in climate science or in population studies where you tend to have low signals relative to the noise. We don't recognize it enough in space physics. So why should we be worrying about noise? Well, we have measurement errors, both in interplanetary space and our geomagnetic index. We don't know the propagation lag exactly, and that can introduce errors. It might be the solar wind you measure at L1 doesn't even hit the Earth. Okay, so that introduces an error. But then a really big one that has been consistently neglected is data gaps. Okay, and the reason that data gaps are neglected is people say, oh, well, their effect averages out. No, they don't. They introduce noise, and then you go and fit to that noise. Okay, so for correlation studies, a data gap is a big noise source. And data gaps were a real problem before 1995, and I'll show you that in a moment. So how do you deal with data gaps? Well, it depends what parameter you're talking about, because the different solar wind parameters have different autocorrelation times. So for example, solar wind speed has such a long autocorrelation time, this is the autocorrelation function as a function of lag, that actually, well, I'll give you the consequences of that in a minute, but compare it to the IMF orientation that changes very rapidly, okay? And so its autocorrelation time is short. So how long a data gap I can tolerate depends very much which parameter I'm talking about. So what I've done here is take data where I had all 6 valid 16 1-minute values in an hour and removed them at random. Okay, and I do that loads and loads of times and then take the average value. And so, for example, let's say I'm interested in having everything to a 2% accuracy. How many samples do I need? Well, for solar wind speed, I only need one. One sample an hour will do. One 1-minute sample an hour is fine for solar wind speed, but for IM orientation, to make 2%, I need to have 58 out of 60, okay? So how much a data gap you can tolerate depends on what parameter you're talking about. Why do I think data gaps are such a problem? Well, this is the overall availability of data before wind and ACE came along in 1995. And it's horrendous, okay? We had a few bits of data between gaps, not the other way around, okay? And it gets much, much better after that. And these are the spectra of the distribution functions of the length, the durations of those gaps. Now, this really matters. What I've done here is I've taken near continuous data. Don't worry about what the fit parameter is for the time being. It's just a single fit parameter and of a coupling function. And actually, I've done it 2 different ways. This blue line, I've taken average values of each parameter, combined them into my coupling function, and then tried to cross-correlate against this coupling exponent here. Oh, for goodness sake, I am sorry. The red line, I actually make the coupling function at high time resolution and then average. Okay, so one is average, then combine, the other is combine, then average. And the red one is actually more accurate. Okay, but beware of that. Okay, they're different, they give you different answers. And they give you different answers for the optimum fit. But then I've taken the distribution of data gaps that existed before 1995, knocked out data at random. I've done that 100,000 times, Monte Carlo'd it, averaged them up, and this is my correlation now. You can see the correlation is considerably worsened, and this is the 2 sigma uncertainty bar. And when I take the optimum value, I now get a spread around that, okay? So it is not true that data gaps do not affect your answer and affect just average out. You've got to remember, I have 100,000 realizations in these distributions. You will have one. You will actually have one series of data gaps. And so you could be anywhere on this distribution. So we have to be aware of the fact that data gaps cause problems. The best way to deal with them, by the way, is to define the data gaps in the interplanetary data, iterate to what the best propagation lag is, and then knock out your terrestrial data at the same time. I call it piecewise removal. And when you do that, then you can actually largely solve the problem. The worst thing to do is to try to interpolate. It makes an awful mess, okay? So in fact, ignoring data gaps is better than trying to interpolate into them. But the best thing is to piecewise remove so that you're only correlating like with like. Now, the parameter I like to use for a coupling function is this power input to the magnetosphere that was proposed by Vassiliounis et al. Way back in 1982. And the reason is it's theory-based, and it's based on the correct theory, unlike epsilon, but it's based on the correct theory. Essentially, this is the kinetic energy density of the solar wind. So multiply it by the solar wind speed, you've got the power flux. This is the area, the cross-sectional area of the magnetosphere that it impacts upon. And then you have a dimensionless transfer function. I do apologize. Leave the touchpad alone. Step away from the touchpad. Okay, the area, the radius of the cross-section of the magnetosphere, you can get from a shape factor, which has to be assumed, times the standoff distance, which we can relate to the solar wind dynamic pressure. And then we use a dimensionless transfer function with this, what is the optimum coupling for IMF orientation factor from the tests that they suggest. But then you have this unknown exponent of the Mach number dependence in the transfer function, and that's your one free fit variable. So the danger of overfitting has been reduced dramatically. So although you end up with an expression that has all these terms in, there's only one free fit parameter, so you're not going to overfit the data. I mentioned epsilon. The reason epsilon is wrong is it's based on the idea that the power arriving at the magnetosphere is in the form of Poynting flux. That's not true. Poynting flux is only a couple of % of the kinetic energy flux. And so it's based on bad theory, and it performs less well than most other coupling functions as a result. I don't know why anybody uses it, okay? It's flawed theoretically, and it really doesn't work well. This is the correlation at 3 hours up to a year, and it's the red line here. It's always worse. Whereas the power input to the magnetosphere is always at least as good as something else, if not better. Down here, something near a year, simpler ones work just as well. Okay, so that's why I like power input to the magnetosphere. So essentially, just to sum up on this, I personally treat all coupling functions that were derived on using data before 1995 as not fit for purpose and actively misleading, okay? The way to deal with it is to do piecewise removal of data there aren't enough samples to meet your error requirement, combine your coupling function and then average, rather than the other way around, and do piecewise removal. Mask out the data so that they cover the same period. You might need to iterate to the optimum lag to get that. Never use epsilon. I like the single fitting parameter of the power input, the Vassiliounis function. And then importantly, if you want to know you're not overfitting, then use the better and more continuous data after 1995 to train your coupling function. And then you can use pre-1995 data for testing, because data gaps are not so a serious problem when you're testing. They're not a big problem like they are when you're training. Okay, this is just to show you how well it works, okay? And there's all sorts of tests that you can do. We've got a nice linear variation, but this is on a year time scale. This is a QQ plot to show the distributions have the same shape. It's homoskedastic, easy for me to say. That means that there's no variation with the fit residuals with either input parameter, which is something that quite often causes problems. So these are tests that you should do. And there's also, you can use the Meng Z test to actually put an error on how good your fit is. This is for a year. This is the same thing for daily data. We've got more scatter, of course, but in fact, the coupling function is better defined. The error is smaller, but there is beginning to be a bit of shape difference between the two distributions. There's a bit of kurtosis creeping into the QQ plot. So one of the distributions is slightly peakier than the other. Okay, let's get back to Russell-McPherron. Why isn't it working as we envisage? You've seen this plot already. This is AM divided up by positive BY or negative BY. And the important thing is the decreases for the unfavorable BY are smaller in magnitude than the increases for the favorable. If I look at the power input to the magnetosphere, that is hardly true. It is true, but only just. So when I average these two together and look at all the data, I only get a very weak semi-annual variation. So the semi-annual variation in power input to the magnetosphere is very small, and yet we have a large semi-annual variation in AM. And this is also true for the occurrence of large events in both cases. Okay, so the same behavior of the two. Now let's go back to the original Russell-McPherron idea, because it said, well, it's this half-wave rectified idea that we have this enhancement at the favorable, but then nothing happens at the unfavorable, so it's flat. And that looks like quite a good matching up to the AM data that's shown here in blue. But then in black, we have this problem. This is the power input to the magnetosphere, and the decreases for these unfavorable orientations of BY are actually, they are smaller than the increases for the favorable, but not by much. And actually, if I use Russell and McPherron's B south, it's even worse, okay? So Russell-McPherron is not working because of the half-wave rectifier idea, okay? Something else is doing it. And very quickly, what I think that something else is solar wind dynamic pressure. We all know that it presses on the nose and compresses the dayside, but it also has an important role in compressing the near-Earth tail. This doesn't happen far down the tail. If I put more open flux far down the tail just expands to keep the field pressure equal to the external static pressure of the solar wind. But where the tail is still flaring in angle, I have an effect of dynamic pressure on the sheath pressure that squeezes the magnetosphere. And that's important because it means when I add open flux to the tail lobe here, the squeezing effect means the field rises. That means I'm storing energy density in a way that can't happen further down the tail. That means the cross-tail current, because this field is increasing, the cross-tail current is increasing. And that is why substorms have to take place quite close to the Earth. You've got to be squeezing the tail, otherwise it just gets flabby and get bigger, and you don't increase the cross-tail current. And of course, eventually this current gets deflected in the substorm current wedge and we get a dipolarization and all that. So the dynamic pressure is extremely important in driving geomagnetic activity. And that's the point that Chris Gertz was making. And if I look at, these are plots of dynamic pressure, it's been normalized, so the average value is 1, against power input to the magnetosphere, again normalized. This is just the number of samples that I have, but this is the average AM. So as we increase the power input to the magnetosphere, we get more geomagnetic activity, but also at a given power input, as we increase the solar wind dynamic pressure, we get more geomagnetic activity. And this is true for these average values, but also for the occurrence of, this is in the top 10% of events, this is the top 5% of events. Okay, so, yeah.
Sorry, we're just coming towards the end. So could you wrap it up in the next minute or so, please?
2 slides to go.
Okay, great. Thank you. Sorry to interrupt.
I can skip that one. This is the important one. Here you have in black the power input to the magnetosphere again. And in red, you have the AM index, but for the lowest tercile of solar wind dynamic pressure, for the middle tercile and the upper tercile. What is happening is that it is not the half-wave rectifier effect that's making Russell-McPherron work, it's dynamic pressure, because the unfavorable equinox is being enhanced from the low value that you would get for the power input by the dynamic pressure, okay? So Russell-McPherron really is not working the way the textbooks will tell you. It's working because of the squeezing of the tail and dynamic pressure, okay? I haven't time to show you this, but the reason that that happens and the reason dipole tilt matters is that you put, in the winter hemisphere, you have more open flux appended to the tail than in the summer hemisphere. And that allows the dipole tilt to disrupt that squeezing of the tail effect. Okay, I shall quit all that. I shall just say that if I put all these factors together, these observed variations, this is what I put in my poster the other day. If I put them all together, I can start to reproduce both the equinoctial pattern and the UT variations quite nicely. So we're beginning to get evidence that this combination of things is really what is going on. Okay, I should stop. Thanks for being patient, and we should take any questions if I've left any time.
Thank you, Mike. That was really, really interesting. We do have a couple of minutes for questions. So if you do have one, just pop it in the Q&A, well, chat box, or use the hands up function. We do have one in already from Maria. So Maria says, interesting talk. You suggested that theories regarding ionospheric conductivity are wrong. Can you elaborate on that?
Yeah, essentially, I've used the AM indices and compared what I see simultaneously in a north and a south. And that gives me a handle for the effect of conductivity on the two indices separately. And when I allow for that, there is an effect for sure, but it doesn't generate the equinoctial pattern. Okay. Now, the theory that says it does is actually a bit strange. The Lyatsky theory says that what matters is you need conductivity in both hemispheres. Now, why? Why would high conductivity in both auroral ovals in both hemispheres give you a larger geomagnetic response? It's actually, I think, counterintuitive. But when I do this study, I don't have time to go over it, but essentially I can get a handle on it by comparing the simultaneous north and south data. And the equinoxes, that they have similar conductivity patterns, but if I take it at the solstices, those two are at different. And so I can therefore work out the effect of conductivity and then substitute it back in, correct the indices. And although there is an effect, it doesn't generate the equinoctial pattern.
Great, thank you. I'm going to jump straight into the next one. Both Steve and John are asking about whether, so you said that around slide 45, that more open flux is appended to one lobe rather than the other. Surely magnetic reconnection opens flux in both hemispheres simultaneously.
It does indeed, and that's quite right. Okay, so if I just take this equinox case here, these mauve field lines are equispaced across the new midnight meridian in the ionosphere, okay? And there are 5 of them threading each lobe here, and there are 2 that are threading the dayside magnetopause, okay? If I take a solstice case like this, here in the winter hemisphere, I've still got 5 and 2 threading the dayside, but I've only got 3 threading the summer hemisphere, and more are threading the dayside magnetopause. What is happening is that because the reconnection site is offset down in towards the winter hemisphere, that field lines moving into the winter hemisphere, both the tension force and the sheath flow bring them quickly into the lobe. Whereas these guys that they want to go this way are hung up because the sheath flow and the tension force, the curvature force, are acting in opposite directions. And they take a long time to actually evolve, even back to the equator and then onto this tail. So you end up with a larger fraction of the open flux, which, as I say, is quite rightly exactly the same in the two hemispheres. Incidentally, the voltage must be the same in the two hemispheres as well, because you've got to be transferring flux at the same rate from the day side to the night side, on average at least. So essentially, you have more flux threading the dayside boundary in the summer hemisphere. And that means the field here is lower. That means the pressure and the energy density is lower. And so the net energy density in the tail here is actually lower than for the equinox case. And these simulations, you can see that in the field values here. The summer hemisphere field is always a lot weaker, and therefore the energy density is weaker. Okay, and it's just because it takes longer to transfer the open flux into the summer hemisphere tail than the day side. And I think that's the source of the equinoctial effect.
Great, thank you. That was really clearly explained. Steve and John say thank you that they've got it now. Okay, I think we should wrap up there. There are a couple of questions, well, one from Nick. Perhaps after I've said bye to everyone, you can stay on the chat and stay on the call and chat about it.
Yep.
So yeah, thank you, Mike. That was a great seminar, really interesting, and brought up lots of really interesting discussion points too. Thank you everyone for attending. This is the last seminar of 2020. We'll kick off again in 2021. So keep your eye on the mailing list for information about that. So yeah, thanks everyone, and bye.